Hello, viewers. This one is about this lecture. It's about compression, which is 1.1.5, 1.1.5 compression. Let us start. There are few key terms. First, let's discuss those key terms. Those are lossless file compression that we are going to study today. Second one is lossy file compression. And then we have, let's first discuss these two. So the thing is that it is often necessary to reduce the file size of a file to either save storage space or to reduce the time taken to stream or transmit data from one device to another. The two common most forms of file compression are these two: lossless file compression and lossy file compression. So what is lossless file compression? With this technique, all the data from the original file can be reconstructed, extracted back when the file is uncompressed. Again, this is particularly important for file where loss of data would be disastrous, such as spreadsheet files or a Word file or any text file or a file which is holding numbers or lectures or notes or whatever, where we need the data exactly the way it was when it was produced. Second one is lossy file compression. With this technique, the file compression algorithm eliminates unnecessary data, as with MP3 and JPEG. You would have definitely heard of these two um, file compression techniques, which are MP3 and JPEG. MP3 is for sound and JPEG is for images. So, lossless file compression is designed to lose none of the original data from the file. And one of the technique that we are going to discuss today is run length encoding, which we generally called R, L, and E. So if you could see here, they also want us to um, know about it. Show understanding of how digital data can be compressed using either lossless, including run-length encoding and lossy data techniques. So lossy file compression usually results in some loss of details when compared to the original. It is usually impossible to reconstruct the original file. The algorithm, means the software that is doing it, used in lossy technique, have to decide which parts of the file are important and need to be kept, and which parts can be discarded. So we will discuss about a few of these formats, MP3 and JPEG, later. So first, let's see how this lossless file compression works, especially with run length encoding. So let us start. run length encoding. So it can be used to compress a number of different file formats. It is a form of lossless, as I told you earlier, uh, file compression that reduces the size of a string of adjacent and identical data, such as repeated um, string maybe, or if it is different data than identical repeated colors, maybe in images or characters in a string. A repeated string is encoded into two values. The first value represents the number of identical data items, such as characters, in the run. The second value represents the code of the data item, such as ASCII code if it is a keyboard character, means that we can see. RLE is only effective where there is a long run of repeated characters, units, or bits. So let's use this RLE with text data. With text data. So let's say we have text, let's say 5 times A, 1, 2, 3, 4, 5, and then we have 4 times B. This is repeated character, and then we have 2 times C and 5 times, let's say, D. So as I said that the first value represents the number of identical data items. In this run, if we could see, it is 5 times uh, ASCII code 97. And this is 4 times ASCII code 98. And this is 2 times ASCII code 99. And this is 5 times ASCII code 100. So this means that we have 5 characters, A, B, C, sorry, A, with ASCII code 97, 4 characters with ASCII code 98, 2 characters with ASCII code 99, and 5 characters with ASCII code 100. Assuming each number in this second row uh, row requires 1 byte of memory. Let's say each number, let's say 5 requires 1 byte, 97 requires 1 byte, 4 requires 1 byte, 98 requires 1 byte, 2 requires 1 byte, 99 requires 1 byte, 5 requires 1 byte, and 100 requires 1 byte. The RLE will need only 8 bytes. This is half the original file size. So it will be saved as 5 bytes if it is text data. One issue that can occur with a string such as, let's say now we have a different string, let's say like CD, then again CD, then again CD, then again CD, where compression is not very effective, obviously. To cope with this, we use a flag. A flag preceding data indicates that what follows are the number of repeating units. For example, if I write 255, where 255 is a flag, and then 5 and then 97, then this 5 would say that there are 5 items with ASCII code 97. Let's see how. When a flag is not used, the next bytes are taken with their face value and a run of 1. So let's consider this string where CD is also there. So let's combine it with repeated elements as well. So let's say we have 8 times A. This is a string. A, A, 3, 4, 5, 6, 7, 8. Then 10 times B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have same CD thing. Three times CD. Let's remove this. And then 8 times E. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. So let's code it first. So this would be 8 times 97, 10 times 98, 1 time 99, this would be 1 time 99, 1 time 100, 1 time 99, 1 time 100, 1 time 99, 1 time 100. And then we have 8 times 101. Remember these 97, 98, and 99, and 100, 101, these are ASCII codes. So if we code it, uh, first we need to realize that the original string contains 32 characters and would occupy 32 bytes of storage. The coded version contains 18 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and would require 18 bytes of storage. Introducing a flag 255 in this case produces this. 255 897, then again 255, 10, 98, 99, 100, 99, 100, 99, 100, then again 255, then 8 and 101. Let me first check it. 255, 8, 97, 255, 10, 98, then 199, 100, 199, 100, 199, 100, 255, 8, and 101. These are now 15 values and would therefore require 15 bytes of storage. This is a reduction in the file size about 53%. So you see, when such happens that we have something like this that is not easy to be converted, what we do, let's say this is the whole string, we will put 255. If it is 255, system will take first as the number of characters and then second as ASCII. Then again 255 number of characters, then ASCII, and there is no 255 further. So everything will be taken as ASCII now. So 99, which is C, and then 100D, then C, then D, then C, then D, and then 255. It means that the next number is the uh, number of ASCII characters afterwards. So 8 times 101, which is D, obviously. All right. So let's say how we can use RLE with images. So using RLE with images. Let's see how. So let's first form a grid of 8 by 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And by 8. 2, 3, 4, 5, 6, 7, 8. So let's say that this is 8 by 8 bits black and white image. All right, so let me write it down. 8 by 8 black and white image. All right, so let's say we have this is filled this way, and then remember one box is 1 pixel. So this image represents, let me make these images corner proper. Okay, so this is F. This is F in 8 by 8 black and white pixel. So if we convert it, it will become, let's say, first let's discuss that the letter F here is a grid where each square requires 1 byte of storage. A white square here has a value of 1, and a black square over here has a value of 0. So if I convert it to the form which is binary, this would become this way. So all whites will become 1. And all blacks will become 0. So this is the binary form. Now let's use RLE. In compressed RLE format, this would become um, 9 whites, as in 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 6 black, 2 whites, 1 black, 7 white, 1 black, 7 white, 5 black, 3 white, 1 black, 7 white, 1 black, then 7 white, 1 black, and 6 white. These are these 6 whites are these 1, 2, 3, 4, 5, 6. You get it? So um, the 8 by 8 grid would need 64 bytes here. The compressed RLE has 30 values. See, 1, 2, 3, 4, 8, 12, 13, 14, 15. These are 15 things representing black and white, and we know that this value is actually the repetition number and this is the actual value. So these will be saved in 2 bytes. So if we have got overall 15, then it means that we need 30 bytes to save it, and therefore need only 30 bytes to store the image. So, so if it is 1 byte, its storage would be um, 64 bytes storage required. This is raw format, and over here we all we need is 30 bytes storage. This is RLE format. Understood? So now this might be also done with um, colored images and all, but that would be um, beyond the discussion of this particular lecture. Now, uh, let's discuss about a few of the lossy formats. You don't have to actually discuss or understand a lot about it, but the thing is that you should know about it. From exam point of view, it has not that it is not as much worthy as this text and black and white format thing. So let's see. What I'm trying to talk about over here is file compression applications, out of which I discussed RLE with text data and RLE with uh, image, black and white image, but that is for lossless. Now over here we are going to discuss for lossy format. So the first one is MP3 or MP4. All right, so MP3 is for sound and MP4 is actually for videos as well. So MP3 uses technology known as audio compression to convert music and other sounds into MP3 file format. Essentially, this compression technology will reduce the size of normal music file by 90%. For example, an 80 MB music file will become 8 MB. So this is 90% using obviously MP3 technology. MP3 files are used in MP3 players, computers, or mobile phones. Music files can be downloaded or streamed from the internet in a compressed format, or CD files can be converted to MP3 format. We all know about it. While streaming, MP3 music quality can never match the full version found on CD, but for the times when internet broadband was not that common, we have seen the use of MP3, widespread use of MP3 always. The quality is satisfactory for most of the purposes, but the thing is that how can the original music file can be reduced by 90% and is still retaining most of the music quality? This is now something wonderful with MP3 clip. So this is done using file compression algorithms that use perceptual music shaping. Perceptual music shaping removes certain sounds, for example, frequencies that are outside the human hearing range. If two sounds are played at the same time, only the louder one can be heard by the ear, so that softer sound is eliminated. This means that certain parts of the music can be removed without affecting the quality too much. MP3 files use what is known as lossy format. Since part of the original file is lost following the compression algorithm. Acha, this means that the original file cannot be put back together again. Obviously, we have lost some of the data, we cannot bring it back. However, even the quality of MP3 can be different since it depends on the bit rate. As we discussed in previous lectures, that bit rate is the amount of each sample bits. Means the number of bits per second used when creating a file. Bit rates are between 80 and 320 kilobits per second. Usually 200 kilobits or higher gives a sound quality close to the normal CD if we use this. Whereas MP4 files are slightly different to MP3 file. This format allows the storage of multimedia files rather than just sound. So music, videos, photos, and animation can all be stored in MP4 format. Videos, for example, could be streamed over the internet using MP4 format without losing any real um, scene quality. And then we have bitmap images. Photographic. All right. When a photographic file is compressed, both the file size and quality of image are reduced, obviously. The common file format is JPEG, which uses lossy file compression. Once the image is subjected to JPEG compression algorithm, a new file is formed and original file can no longer be constructed since we have lost data in it. JPEG will reduce the raw bitmap image by a factor between 5 and 50, depending on the quality of the original files. The thing is that while we are creating JPEG files, it is in our control that what and to what extent data we want to reduce. For example, we may want to reduce number of pixels, we may want to reduce the colors per pixel and all. Whereas in vector graphics, vector graphics can also undergo some form of file compression. Scalable vector graphics, as we know that the format is SVG, scalable vector graphics, are defined in XML text files, therefore therefore allows them to compressed. So this particular slide here is not that important from A levels point of view, but yes, from O levels point of view, it has some worth in it. Uh, anyways, so general method of, let's discuss general methods of compressing files. So the last thing that you need to know, afterwards we will go and see some past papers. General methods of compressing files. Now, whatever the techniques that we have discussed are excellent for a very specific type of files. However, it is also worth considering some general methods to reduce the size of a file without the need to use lossy or lossless file compression. So, what could be that? Remember, such thing might be the um, part of your exam question. So let's say we have got movie files. Movie files can be reduce the sampling rate used. Sampling rate used could be reduce the sampling resolution. Could be reduce the frame rate. What I'm trying to imply over here, that what if they ask that instead of using lossy or lossless file compression, what could be the way to reduce the size of the file? So let's say, let's talk about image files. Image files may crop the image. It will significantly reduce the size of file and decrease the color depth. And thirdly, reduce the image resolution. So instead of going for lossy compression, we can imply these few things to reduce the size of files. Whereas in lossless, we can always bring the thing back. So let's discuss a few of the past paper questions. So this is from May, June 15, a question from both P11 and P12. Explain the difference between lossy and lossless data compression techniques. They both are used to reduce the file size, and in lossless, we bring the file back to the form where it was, and it is mostly necessary for text data that we have typed and number data like in spreadsheets and all. Whereas in lossy data compression, we use lossy data compression where it is okay to reduce some of the data and still we don't notice it, like the sounds beyond the ability of hearing uh, of humans, and colors which we cannot see anymore, the depth of pixels over the screen, and so on and so forth. But the lossy data technique, whenever it is used, the data that is lost cannot be recovered. All right, so ON15 images can be compressed to reduce file size. Describe how lossless compression technique works. Describe how lossy compression technique work. This is what we have already discussed. So let's see this question. A group of students broadcast, this is from MJ16, P11, P12 both. Uh, a group of students broadcast a school radio station on a website. Record, they record their sound clips programs in advance and email them to the producer. The student use software to compress the sound clips before emailing them. Circle um your chosen method of compression and justify your choice. All right, so we can go for lossy as in sound. If we lose some data, as we have just discussed with MP3, we can still hear it in a good quality. Plus, MP3, since it reduces to mm, 90%, and whatever is left is just 10%, we can transfer it fast because they are going to send it through email and all. Uh, Students also email images to radio station for use on its website. These are compressed before sending using run length encoding. It is lossless, so it's gonna get back to the original form. Explain what is meant by run length encoding. I explained it that system reads every data unit in a run from the start to the end and tries to find repeated elements, and more the repeated elements, better the run length encoding works. Rest you can see in notes, they are there. The following diagram shows the denary color code that represents each color. Black B is 153 and W is 255. The first three rows of the bitmap images are these. So we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Bs, 1, 2, 3 whites, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 Bs. So let's write it. One, two, three, four, five, six, seven, eight, nine, 10. So 10, 153, 1, 2, 3, 3, 255, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, 153, 1, 2, 3, 4, 5, 6, 6, 255, 1, 2, 3, 4, 5, 6, 7, 8. 8, 153, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 255. So we need 1 byte, 2 byte, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes. All right, show how RLE will compress the first three rows of this image. So they want it row by row. So there we go. Let's do it row by row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 153, 3, 255. Then we have got 3, 153. This is first row. And in second row, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 153. Then 1, 2, 3, 4, 5, 6. 6, 255. And then 1, 153. That's second row. And then in third row, 1, 2, 3, 4, 5, 6, 7. 7, 153. 1, 2, 3, 4, 5, 6, 7, 8, 9. 255. So students, that's it. I hope that you now realize that what is file compression, what sort of file compression we use, and what sort of data can be compressed using what, how RLE works. And I tried to explain with images, with sound, with text, and I discussed in length about RLE, if it is um, implemented over the text or if it is implemented over the image. So I hope that you would have now great understanding of file compression and its reasonings and techniques. So until next time, bye.